This is an important homework problem because it's just like the one of the assignments that you have. So how does it go? You have this problem. Is it large enough? To solve, okay? So what you're trying to find is some non-negative integer values for x1, x2, and x3 that would maximize a certain thing. So I'll call this problem S. And you start by, because it's branch and bound, you'll be creating your branching tree. At the top, you have the problem S. What you keep track of is all the unsolved problems. Okay, so there's S on it at the moment. Another thing you keep track of is the incumbent solution, which there isn't any yet. So the incumbent means the best integer solution found so far in the course of the algorithm. And then best bound is its objective value. So far you haven't found any, so the bound is minus infinity. You have absolutely no idea about how good your solution is going to be. Okay, so it's certainly going to be better than minus infinity, but that's the only thing you know in the beginning. So what you do next, once you've set up everything, is you solve this problem, but without integrality. So instead of here, for something that's called the ILP relaxation, you just take x1, x2, and x3 greater than or equal to 0, but you ignore that they should be integer. Right? How do you solve it? Any way you want. But probably the fastest way is you type something like this into Mosul. Okay, but this is kind of optional. It just prints the solution and it prints that the problem is infeasible if it's infeasible. But what is important is you have your decision variables, the three constraints, and the objective like this. And if you do it in Express IVE, then, well, you can check in the matrix and called overview and all these things on the right. What the solution is if you don't put this in. But yeah, if you put this in, it prints the solution immediately. So when you do it for this problem S, what it's going to do is it's going to right, Z is 21.7 something. X1 is 0.0 something. X2 is 7. And X3 is 0.6. Something like that. Okay, so this is the solution. It's not all integers because this one is, well, it's 0.0, but there are some other digits. So because it's not integer, you just note it here that the best 7.5. Oh no, what have I done? I've read the, I apologize. Not 0.6. Okay, I've read the wrong place. So actually, it's going to give you x1 as exactly 0, and x2 is 7.5. I was looking at the wrong problem. Sorry about that. But anyway, so you put that. You take note of what it produced. So this is not all integer, and the z is 22.5. And because it's not all integer, and there's The other thing that you could do to stop branching, you have to branch. So you create two subproblems, and I'll call them S1, and the other one I'll call S2. For example. Now, what you look at is some value which is fractional, and by a rule of thumb, the most fractional one. So this would be this 7.5, and you add two constraints. So on the left, you add is no more than 7, x2, and on the right, you add is greater than or equal to 8. Okay, now S has been solved, but you add S1 and S2 because S1 and S2 are unsolved problems. And so this is like a step that you do every time, as long as you have some unsolved problems. Okay, so you continue. What you do next is look at your list of unsolved problems, pick S1 or S2. Which one do you want? Which one would you do first? S2? Okay, so you pick S2. So what you do is in this code, x2 is greater than or equal to 8. You need to add the constraint. So here you add x2 greater than or equal to 8. And you run this code again. And what it tells you is that this is infeasible. This is somehow strange. I've got the wrong problem here. I've done something wrong somewhere, because these problems don't solve the question that I have here. So I've taken the solution of something completely different. But I don't know why. What have I done? So the model solution that I've brought for myself is clearly not the solution to this particular problem. So forget it. I'll bring the right one next week. My apologies. I mean, the principle is always the same, but for some reason, I don't know what I've done. Sorry about that. I brought the wrong solution, so I'll bring the right solution next week. Now you know what to do. You have another week to, and then of course you normally solve the homework exactly. That's embarrassing. Very strange. Okay. Let's do something else then. I think I'm getting old. Okay, this is still a leftover from last week, what I kind of was planning to do last week. So it's in last week's handout. Do you need it? You need one. I think I've got it. Okay. Just got one.
Oh, it's not right. Quite well.
Yeah.
Oh,
Well, hopefully I can get this one right. Register. Okay, so how does this go? Is the question clear to everyone? No? Okay, what I'm looking for is, I've got 3 different telecom companies that I can choose from. I can take a subscription from 1 of them, 2 of them, or 3 of them. If I take a subscription, I will be paying this fixed amount per month. But I'll get some free minutes with it. And then any additional minute that I take with them is going to cost me 32 pence or 23 pence or 21. And what I have is I want to make 500 minutes of calls. I'm trying to find the cheapest solution possible. I usually summarize what is kind of known. So we have a set of telecoms, what I call all 3, lemon, and 4. And I have fixed charges, 3 minutes, cost per minute, and 500 minutes. So I'll say M is 500 minutes. Just to have a letter for it. And I can say FI is the fixed charge. For each of the, so I will have 3 different values, depending on which telecom I'm looking at. The 3 minutes, I'm calling MI. Because that's what I have in my notes. And then I have these additional costs, so CI. Will be the cost of a non-3 minute with each of these telecoms. Okay. That's how it goes. And then what do I need? Decision variables. Any suggestions about decision variables? George?
X 1, 2, and 3 for each of the phone companies where you do want to not choose it. Like 1 or 2.
Okay. X1, X2, X3, you might call them. I'll just say XI, whatever I is. And whether you choose it or not. So how would you put it? How would anybody else put it?
Let's do a 7.
Yeah, so you want kind of suggest an interpretation that it's 1 if we subscribe to that telecom. And 0 otherwise. So that's your idea. Okay. Any other decision variables that would be useful? Okay.
Number of minutes purchased from Telecoms. Subscribe.
Okay, number of minutes. Purchased from that telecom. Any letter you want?
Yeah.
The specific one?
P.
P? Okay. Any more decision variables?
Cost of the minutes purchased or cost of total fixed charge.
Could do. So cost of what exactly?
Fixed charge plus not a minutes purchased, I guess.
So like money spent with a particular telecom? Okay, could do. So what do you want to call it?
What letter?
Yeah.
J.
J. So for that particular telecom. You can have it if you want. I won't ask for any more because it's only getting more complicated. So the objective we were told should be to minimize, this is with each telecom. The objective we were told was to minimize the total cost. We need a formula for the total cost. But we know that for each of the telecoms it's JI, so we just need to add them all together. Okay. There shouldn't be any problem with that. And any constraints?
sum of xi times the bracket mi plus mi is equal to 500.
Say it again. The sum of
The sum of xi times the bracket mi plus fi. So the fixed minutes plus the ranging minutes
like this.
is equal, yeah, is equal to 500.
Well, 500 was big M, so let's stick to big M. Okay, and the sum is overall telecoms. So what does that mean? What's the purpose of this constraint?
So the resulting minutes of all, the resulting total of all purchase minutes is only equal to 500. That's what's required.
MI plus FI, is that what you said?
Yeah. MI is the fixed.
MI is the 3 minutes, and FI is the fixed charge.
Oh wait, no. Yeah.
No, CI is the
No,
cost per non-3 minute.
Yeah.
Something's wrong there. Oh, we want the PI here. Yes. Okay. So what does that mean? These are the 3 minutes. These are the non-3 minutes. Add it together, and what do I times it by SI?
But you chose.
That's true. There's a problem with this constraint. You'll have to pay for it. I won't let you do that. And I won't let you do that because we're trying to write linear programming, interlinear programs. So linear means that you can't have product of 2 decision variables. So that's 1 decision variable, and you're timesing it by another decision variable, which is making it a quadratic program. So, like, yes, I trust you. You could write your formulation with this constraint, but it wouldn't be linear. And solving quadratic programs is computationally harder than solving linear programs. So we want to avoid that. Okay. But it's a good thing to know. So this won't work because we want linear constraints. XI times PI. Does it make sense what I've just said? Yeah, we want linear programs. I mean, if you were allowed quadratic constraints, that would be a perfectly good constraint. But we don't want them, so we have to do something else instead. So not this, but okay, I'll give you the right one. So what you want is xi times mi. That's perfectly legal because mi is a constant. It's just a number of 3 minutes, and that's part of the data, so you can times that. And then you just add the number of non-3 minutes, like that. And you don't have to times it by 0 or 1. And that added all together should be equal to the 500 that we need. This one's linear, but there's a problem, right? There's an additional problem which wasn't there in the first constraint, which is that we somehow have to make sure that we're not using any of the non-free minute unless we're paying the subscription. Okay? Because so far we haven't got a constraint that would make sure that this thing is 0 when we're not subscribing and xi is 0. So we need to make sure and for this, we can do it with a linear constraint, which says that this pi is no more than m times xi. So what does this constraint do? Well, if xi is 1, it tells us that we shouldn't take more than 500 minutes from that particular telecom, which is okay because we don't want to take more than 500 minutes. So it's not doing anything really. But if xi is 0, then it's telling us that we shouldn't take more than 0 minutes from that particular telecom, which is exactly what we want. Okay? So if xi is 0, this constraint ensures that pi is also 0, and if xi is 1, it doesn't limit it in any meaningful way, other than what we wouldn't have from that constraint. That bit. Any questions? Can you explain it that way?
We did. I just thought, wouldn't it be like mxi minus mixi? So it's minus the 3 minutes that you've already purchased, so it doesn't even go for like, what is that already?
What would that? Like you could put a million xi there, 2 billion. It really only serves the purpose to ensure that if xi is 0, this right hand side is 0. If xi is not 0, and we don't care what the right hand side is, but it must not be too small, so it would limit us in taking more than 500 or 300 or whatever. And so if m is large enough, larger than 500, or at least 500, or at least, and that's okay. But it's okay to make it larger than just 500. What we shouldn't do is put 100 there, because that would put a constraint that we shouldn't take more than 100, not 3 minutes to any telecom. We don't want such a constraint. The only concern is to make this n this constant large. So you can put a slightly smaller one, but you don't need to. Okay, so that's this. And then and then there's this complication with the j. So we should make sure that this j is actually expresses the amount of money that we spend with that telecom. So the amount of money we spend with that telecom is, well, if xi is 1, then we have the subscription charge fi, and we're also paying for each of the minutes, like that. Okay. Yeah, cost of 1 minute, how many minutes we're taking of the non-free ones. Fixed charge, 0 or 1, whether we're taking the fixed charge or not.
Not CI, PI.
Yeah, it should be. You see, I've got the same problem. Thank you. Yeah, that's the paid minutes. So it's CIPI. And that should do everything, I think. Other than we still didn't say that this variable has to be binary and this pi should be non-negative. There is no particular reason why we should want to make it integer. So we can have this kind of thing where some of the variables are allowed to be non-integer. Because you can do half a minute or you can do a quarter of a minute. That's not a problem. So when you have something like this, where some of the variables are integer, and this one can be fractional, and it's called a mixed integer programming formulation, so mixed. Mixed. Because it's a mixture of integer and fractional. It's mixed. Okay, any questions about this problem? You probably start to be lazy because then less and less every day. Yeah, this is a fairly complicated problem, but nice one. So what we're trying to do is we have some projects. It doesn't give us any specific data in this handout, but we can just work with this kind of formulation as it is. For every project, we know how much of a certain resource it uses, and also how long it lasts. So, for example, you could have a project project 1, its duration, I'll call it D1, is 3 months. And the resource that it requires is 3 units in the first month, four units in its second month, and 2 units in the third month. So this is the requirement of the first project in the first month. This is the requirement of the first project in its second month. And this is the requirement of the first project in its third month. I'll call them R project month. So you will have a number of projects, and for each of them you will know how long they take from start to finish, and how much of a certain resource they use, whatever that resource is. Could be the number of excavators or something like that, depending on what these projects are. I'm not going into any specifics with that. But you also know that as soon as the project is finished, it's giving you some benefit. So once you finish it, you're earning £10,200 or something per month from it. Okay. And then there might be other projects whose benefit is larger, and so you want to finish them earlier, hopefully, and other ones whose benefit is smaller, so you might want to wait, because the longer, the earlier you finish it, the longer you're earning this money. Okay? That's quite a complicated thing. So that's project one, and then there might be, there are other projects as well. And then another thing we know is for the coming 6 months, 1, 2, 3, 4, 5, 6, we know how much of the resource is available. So in the first month, it's 5, then it's 6, then it's 7, and 6, and 6. As an example. So in a typical real life situation, this is just simplified so we can actually solve it. In a typical real life situation, you won't have just one type of resource, or you might have many different types of resources, because it's people, it's some machines, other machines, I don't know what, depending on what kind of project it is. Okay? And then you would have this availability for each of those resources separately, and also these requirements for each of those resources separately. But just to keep it simple, we only have one kind of resource, and generalizing to several resources is very straightforward. We just have a separate set of constraints for each of the resources. So this is the setting. The question is, we have to plan. So we have to decide when to start each project of the set of projects that are described. And we must set them in such a way that in no month we're using more from the projects that are currently running. We would be using more than this available amount of the resource. Okay. So the way this is done in using integer programming is kind of tricky. So this is an important trick, really, is that you will have a decision variable called, I'll call it S for start, SPN, which is 1 if project P starts in month M. And is 0 otherwise. Perhaps without knowing this trick, one would be tempted to have a decision variable which takes values 1, 2, 3, 4, 5, or 6 for each of the projects, which gives you the month in which it is starting, but it's almost impossible. It's kind of impossible to write it with these decision variables. So the right way to do it is to have a binary variable for each combination of project and month, which tells us whether this is the month when the project starts or not. But because the time is up, we'll finish this formulation next week. You have a homework, which is to have a look at the modal code for for something that we did as the first problem, which was transporting things on a ship. So yeah, it would be good if you came to the labs in the morning and to have to refresh your model. My homework is to solve last week's homework and bring the right solutions. And other than that, enjoy your week.